So for this one, it's looking at asking us which bromide below is most likely to lose Br minus and form an aromatic carbocation with a positive charge is stabilized by resonance. So what you need to do actually is not look at these. You actually need to show this happening for every single one. The carbon-bromine bond breaks. So I'll do that first. Okay, so I just went ahead and had the carbon-bromine bond break for all of these. And then I drew the resulting cation. And what they want us to look at here is which of these cations is going to be really stable. So which of these reactions is likely to happen, right? So anytime a reaction takes place, one of two things is true, or both. Either you have reactive starting materials, reactive bonds, and or stable products. So in this case, all of these are carbon-bromine bonds, so not much different really. But the stability of the products is going to be very different. So for this one, this is a ring, an uninterrupted p orbital system with an even number of pairs of electrons. So this would actually be anti-aromatic. So that's not very likely to happen. Right? That's an anti-aromatic species. The next one over, also uninterrupted p orbital system, right? Carbocations are sp2 hybridized, so they have an empty p orbital, right? 1, 2, 3, that's an odd number. So this is actually aromatic. So that's really good. That's a really stable product. This one has resonance, but if you notice there's an sp3 hybridized atom here, so this is not going to be aromatic, it's going to be non-aromatic. So it's not terrible, but it's not as good as being aromatic. And then the worst one actually is this one, because you have an empty sp2 hybrid orbital that can't do any resonance at all. Right, at least this could do resonance, this can do resonance, this can't do resonance at all. So this is really bad. So this is like never going to happen either. So the answer they want is making an aromatic product. So right, again, D can't do resonance because the empty orbital here, like what happened, which hybrid orbitals were making this bond? It was this carbon's sp2 hybridized. So there's a p orbital and 3 sp2s. Its p orbital is being used to make this pi bond. So this bond is being made with an sp2 hybrid orbital. So that's the one that ends up being empty here. And that can't do resonance. Only p orbitals and pi bonds can do resonance. So hence, that's why this is not very stable at all. So here's an example we had of a compound, a strange looking species, but we're trying to look and decide if it's aromatic or anti-aromatic or non-aromatic or neither. So we gotta remember the rules for aromaticity. Has to be in a ring, so it's definitely in a ring. Has to be an uninterrupted p orbital system, meaning no sp3 hybridized atoms. So if you look at these two carbons are for sure sp2 hybridized. Now this one is also sp2 hybridized because it wants this p orbital to be able to do resonance. Same with this carbon. It also is going to be sp2 hybridized. So these electrons are all in a p orbital system. And what that means then, how many pairs of electrons are there in that orbital system then? It's 1, 2, 3. That's an odd number of pairs. That's what makes this aromatic, right? Uninterrupted, odd number of pairs, in a ring. So it's aromatic. It looks strange, but these are going to be in p orbitals. These carbons are going to choose to be sp2 hybridized, so they have p orbitals to put the lone pairs in, and that's going to allow it to all be in one uninterrupted system. 1, 2, 3, odd. So according to Huckel's rules, this compound therefore is aromatic. So just kind of knowing those rules is the key. And I always think if you forget, just remember benzene's aromatic and think about what the traits of benzene. It's a ring. There's no sp3 hybridized atoms, and it has 1, 2, 3, has an odd number of pairs of electrons. Pairs, right? So that's always a good one to kind of look at to remember versus like memorizing the rules, I think. Okay, so taking a look at kind of this alkylation and different ways you can do alkylations with different alkyl bromides. So I showed an allylic, a benzylic, and then bromobenzene, and they're all going to react with iron bromide. And some of them are going to work and some are not. And what's going to happen here is essentially what we'll find out is these two are okay forming carbocations, whereas this one's not. Because what kind of carbocation would this form? This one's going to form a carbocation with an empty sp2 orbital that can't do any resonance. Whereas this one, this benzylic, it's going to form a primary carbocation, but it's primary and benzylic, so it can do all that resonance in the ring, right? The electrons can come out of the ring. Same deal up here. You're going to form a primary carbocation, but it's primary and allylic, so it can do resonance. That's what makes a difference. So really kind of look at Friedel-Crafts alkylations are good if you can have a stabilized carbocation. So things that are sp2 or sp hybridized don't work for this. And that's what I was saying now, is that things that when you have a bromine or halogen on an sp2 or sp hybridized atom, you need to do a special type of reaction called with an organometallic reagent. So using things like palladium to do those couplings. So we used to not be able to do these, and so it's been a big achievement to be able to do those and open up new molecules and syntheses for all types of stuff. So basically, Friedel-Crafts only works for things that can be stabilized carbocations. This can't. Got a good question. So things like that don't have lone pairs, right? So things like ethylbenzene or toluene, why are they considered electron donating groups? So now, to be fair, they're not great electron donating groups, but they still donate electron density to the ring. And they don't do it with lone pairs, they don't do it with pi bonds, they do it through hyperconjugation. Hyperconjugation, right? That's those sigma bonds 2 bonds away, and they can help donate electron density. So even if you think of all right, here's the benzene ring, right? You got the p orbital system there all lined up. You have this sp3 hybridized atom, right? Right. Even though these aren't perfectly lined up, right? And this is a 109.5. It's kind of like at an angle, but it's kind of semi-donates electron density. Each one of these can donate electron density towards the ring. Not a lot, but it's better than nothing, right? So hyperconjugation is the reason why these are electron donating, because of this orbital interaction. Same reason why you stabilize a carbocation with hyperconjugation. Now we're just talking about with it into a ring. So say I had something like this, and this is another way of thinking about resonance and with the likelihood of resonance and which atom's going to do it. Because you could also translate something like this to something we talked about in class 2. Like if I have these two things on the ring, they're both electron donating groups, but which one's more important? Well, the difference between nitrogen and oxygen. What's the difference between those two? Oxygen's more electronegative. So I would guess it's less likely to donate. So this nitrogen is going to be the more important one. So it's going to direct ortho and para to it, right? The most important electron donor, because it's going to be willing to do resonance more. So back over here, you have both a nitrogen and oxygen. They both could do resonance. Which one's more likely to do resonance? The less electronegative one, right? Because it's more likely to donate electrons. So I would guess this would be the dominant resonance form, because the nitrogen is more willing to donate electrons. So this would be the dominant form. Just like this is the most important donating group because it's more willing, less electronegative to donate electrons versus the oxygen. So I expect things to go ortho and para, and it can't go here because it's already spot, it's covered.